On the night of August 21st, 1986, a lake killed more than 1,700 people. Lake Nyos in northwestern Cameroon showed no lava, no ash plume, and no obvious eruption. Villages below the crater simply went silent. People collapsed where they slept or walked. Cattle and other animals died across the low ground. Survivors later described waking weak and confused. Sometimes many hours later, oil lamps had gone out even though fuel remained. The killer was carbon dioxide. A vast amount of the gas had escaped from the lake, spread through valleys, and displaced the air people needed to breathe. Because carbon dioxide is denser than ordinary air, the cloud followed low terrain instead of dispersing quickly upward. The disaster reached settlements several kilometers from the lake. Yet the pattern was uneven. Low-lying homes and animal pens could be devastated while higher ground nearby offered a better chance of survival. By daylight, Nyos still looked deceptively calm. There was no fresh volcanic crater, no river of lava, and no simple explanation visible at the surface. Investigators had to look downward into water more than 200 meters deep. The most dangerous part of the lake had been hidden from view. Lake Nyos occupies a volcanic crater, but the disaster was not a conventional volcanic eruption. Carbon dioxide from deep magmatic sources had been entering groundwater beneath the region and feeding the lake from below. In a shallow or frequently mixed lake, much of that gas could escape gradually. Nyos was different. Its deep water was cold, dense, chemically distinct, and poorly mixed with the surface. Pressure increased with depth, allowing enormous quantities of carbon dioxide to remain dissolved, much like gas held inside a sealed bottle. The tropical setting also helped the deep layers remain isolated for long periods instead of overturning each winter as many temperate lakes do. Over years, the bottom water became increasingly charged. The danger was almost invisible because the upper water could remain ordinary, while the deepest layers stored more and more gas. 2 years earlier, nearby Lake Nyos had released carbon dioxide and killed 37 people. That tragedy showed that Cameroon possessed a rare kind of volcanic lake hazard, but Nyos revealed how extreme it could become. After the 1986 disaster, scientists repeatedly lowered instruments and sampling equipment into the lake. Their measurements showed that carbon dioxide was accumulating again in the deep water. The lake had survived the release without losing the process that created the danger. The exact trigger of the Lake Nyos disaster is still debated. A landslide has often been proposed, while other disturbances and even the possibility of a spontaneous instability have been discussed. What matters most is what happened after gas-rich water began moving upward. As the water rose, the pressure around it fell. Dissolved carbon dioxide then started coming out of solution as bubbles. Those bubbles made the water less dense, so it rose faster. Faster rising water experienced still lower pressure and released still more gas. A small disturbance could therefore become a self-accelerating chain reaction. The lake effectively began to overturn from within. Gas and water surged upward, and carbon dioxide escaped at the surface in enormous volume. The gas itself was invisible, even though disturbed water, spray, or condensed moisture around the lake could be visible. Once released, the carbon dioxide spread downhill through valleys and depressions. Investigators found a pattern consistent with this behavior. Low areas suffered catastrophic mortality, while some people and animals on higher ground survived. Chemical, isotopic, and geological evidence also argued against a new magmatic eruption that night. No fresh pulse of lava was required. The lake had not suddenly created the gas. It had stored it, under pressure, over a long period, then released it with devastating speed. That discovery created a frightening engineering problem. Lake Nyos was still being recharged with carbon dioxide after 1986, so simply waiting meant allowing the reservoir to rebuild. Scientists and engineers therefore tried to reverse the same physical mechanism that made the lake dangerous. The idea was to place a pipe deep into the gas-rich water and bring some of that water upward in a controlled pathway. Once the rising water reached lower pressure, carbon dioxide formed bubbles inside the pipe. Those bubbles reduced the density of the water column and helped pull more deep water upward. So after flow was initiated, the system could continue with little external pumping. Experimental degassing work in the 1990s led to permanent controlled degassing at Lake Nyos in 2001. Monitoring showed that the process reduced the lake's gas inventory without creating the feared dangerous instability, although researchers concluded that one pipe alone was too slow to remove the hazard quickly. More capacity and continued monitoring were needed because carbon dioxide continued to enter the lake from below. The deeper lesson was remarkable. The same pressure, drop, and bubble formation that had full landscape can store an invisible physical threat, and that understanding the mechanism can turn part of a disaster's cause into part of its solution.